Okay, good afternoon, everybody. Welcome to the afternoon session of our conference. So the first speaker is Armengol Gasull. He's a professor at the mathematics department at Universitat Autònoma de Barcelona. He's also a member of the Dynamical Systems Group, this university, and also a member of Central Recerca Matemàtica. His research fields are dynamical systems, particularly ordinary differential equations. He also works in planar differential equations, global asymptotic stability, global injectivity, mathematical modeling, and difference equations. So Professor Gasull will talk about dynamical Parrondo paradoxes. So Armengol, whenever you want, you can start your talk, and thanks so much for being here with us.
Thank you very much for the opportunity to talk here. My talk is about dynamical Parrondo paradoxes. This talk is based on these three papers. The first two papers are we did at the beginning. This is the first one is about discrete models, period discrete models. I will define exactly the setting. And the second one is about differential equations. Both study the so-called Parrondo dynamic paradox that I will define in a moment. And the third one is something that was left in the first works about dimension 3 counterexamples of things. So, and this is a more recent work. And study, while the first two are mainly about analytic differential equations and the computations count. The third one is about homeomorphisms. So we have nothing, we have no derivatives, no Taylor expansions, and is more topological one. And also in the third one, we will see some random component of the dynamics. So this is the talk. First, I will explain what is not the dynamical, but only the Parrondo paradoxes. And then in a few words, then I will consider in this talk three. This is the discrete Parrondo paradox, the Parrondo paradox for iterated function systems, where here there appear some probabilities and so on. And the fifth point is about the part of differential equations. And I will say something about some proofs also here in this step here. So I start. What is the Parrondo paradox? The Parrondo paradox is something in game theory that and shows the situation is more or less like this. You have some strategy, and what is clear is that if you used iteratively the same strategy, you lost all your money, for instance. And you have another strategy that also that if you follow this strategy, you lost all what you have. But if you combine, and here combining means first one strategy, then the second, then the first, then the second, and this alternating, and then you have a winning strategy. I have not studied in detail this paradox, but I know that it was proposed in a meeting and then becomes famous because of this paper in Nature 3 years later. So when you explain something somewhere, maybe someone is hearing you. So you have to take care. And from this point of view, in some moment we decide to fix a related problem. Why don't change winning by attracting fixed point and losing by repelling fixed point? So I will say that a dynamic Parrondo paradox arises if you have a discrete dynamical systems, a discrete one that if you iterate this near a fixed point, then you go to the fixed point. But and you have two of these discrete dynamical systems that are given by maps. But then is it possible that maybe when you iterate first F, then G, then F, then G, then F, G, in this periodic way, you get a repelling fixed point? This is the if this happens, I will say that I have a Parrondo paradox. And I will present this kind of paradox in what is called periodic discrete dynamical systems. That this essentially says take a finite number of functions, let's say 3 functions, f, g, and h, and then you start doing first f, then g, then h, f, g, h, f, g, h, and you are interested if this kind of Parrondo paradox arises or not. We'll see that depends a little on the dimension where you are. If you are in dimension 1, 2, 3, 4, or you take only 2 maps or 3 maps, and so on. The iterated function system is something similar, but in some sense more complicated, but also very interesting. That assume, for instance, that you have only 2 functions again, but then before deciding the map that you apply, you threw a coin. So you take f, for instance, you throw a coin, you say, oh, f, then another throw a coin, then now g, then a coin, now g. So, and you have p and q, the probabilities of f and g, and you want to know if in this more complicated setting also is possible or not that Parrondo dynamical paradox happens. And the answer is yes, also happens here. We will see this. And the third setting is we thought, what about differential equations? And what is now the alternating? No, so this is like you put a clock in your table, and each minute, let's say, you go by the flow of the first equation for 1 minute. Then you, after 1 minute, you change the equation. You take the second equation. 1 minute later, you take again the first equation, and you combine in this way 2 or more vector fields. And the situation is you can have a change of stability or maybe not when you have this kind of situation. So in all this talk, when I am talking about Parrondo dynamical paradox, I'm meaning this combination that maybe discrete dynamical system maybe flows at fixed time, maybe you threw a coin to decide the map. So I first a comment that there are other papers about also the same name, but another situation where the authors take maps that have simple dynamics, and combining them in periodic way, you get complicated dynamics, even chaos. Also, people call this dynamic Parrondo paradoxes. But this is in our study, we also only study fixed points or critical points and what happens near this point, let's say. This is more a global Parrondo paradox. The tools are totally different, only the name is the same. So let's start the first part about the discrete Parrondo paradox. The discrete Parrondo paradox, the setting is a setting that is very well studied in models on biology, and this is just that you have mathematically just have this difference, this iteration process where you see this f is changing at each step. So x1 is f1 of x0, then x2 is f2 of x1. So the f is changing, but moreover, there are finitely many of these maps that appear in a fixed order. And so this k is the period of the discrete dynamical systems. Of course, these models are very fit very well in seasonality situations. For instance, you have 2 maps, you have winter and summer, winter, summer, winter, summer, and so on. This is the but for this discrete dynamical systems is well known that to study this non-autonomous, because you change the map each time, but periodic is the same. Is very related to study what is called the composition map. That is simply you consider k steps, and you take this fixed map, and so you have no more non-autonomous. You can have a autonomous discrete system where you have this composition map, and this composition map studies only what happens after a complete cycle of k steps, and then you repeat. So this is non-autonomous in the middle, but globally it's like autonomous. But in this point of Parrondo paradoxes, what we have is the setting is F1 has a point that is an attractor, F2 also, F3, F4, all the F have a point that is a local attractor, and I am interested to know if the composition that is this map has also and can have a repeller. This is the point. So this is the problem. You have a fixed point that is common in all maps. Of course, I am not talking, it's possible to do this with periodic orbits and others, but I am always in the simplest situation. You have a fixed point that is locally asymptotically stable for all the maps, and I want to know what can happen for the same point, but for the composition map. This is all. This is for the global system. And the answer, we will see that depends on the dimension where you are. If we are in R2 or R3 are different. The number of maps, so the period, and also is very important to take into account if the points are hyperbolic or not. As we will see, the Parrondo paradoxes for hyperbolic points never happen. So in general, you have no this strange situation. So hyperbolicity is one of, we need loss of hyperbolicity to have this paradox. So I give some idea of the proof now, and also some examples to have an intuition. Of course, the first thing that people did, this is in this paper with simple examples, is for linear case. In this, just simply take two linear maps, this map A1 and this map A2. These are linear maps. The origin is the common fixed point. It's clear that here the eigenvalues are alpha for both maps. So the point is globally asymptotically stable if and only if alpha is in modulus is smaller than 1. This is trivial because it's linear. But if you do the composition, this is first A1, A2, and you repeat this periodically, so A1, A2, A1, A2, and so on, the composition map is a linear map, but now the stability of the origin, the eigenvalues have been changed to these ones, and we have that if alpha is smaller than 0.61, then the origin keeps the stability. Here was global attractor. Also for the composition, you have a global attractor. But in the complementary case, when alpha is bigger than this point, then you get a saddle. So there is no problem to lose the stability. So this is not Parrondo paradoxes. You have two global attractors, and you combine, and you get a saddle. This is very intuitively that you have some direction where you can escape, because depending on how are the linear maps, you can imagine that this is, and it really is very easy to see that this happens. So this is what happens in the hyperbolic case, because in the hyperbolic case, essentially, the linear part is the one that says what happens, and also we have always this situation. I give a sketch of the proof that in the hyperbolic case you have no Parrondo paradoxes. So I will prove that if I have a point that is locally asymptotically stable for all the maps, P is never a repeller for the composition. I will prove in next slide. And in dimension 1, if all the maps have a point that is locally asymptotically stable, then the point for the composition map also is the same. So in the hyperbolic case, no Parrondo paradoxes at all. The proof is very easy. For instance, here's the proof. You take a point that is locally asymptotically stable and hyperbolic for all the maps. So for any map, this determinant of the differential of the map is the product of all the eigenvalues. Maybe here I should put lambda 1i, lambda 2i, lambda mi, because depends on the point, but doesn't matter. Only take that the determinant is smaller than 1, because all the eigenvalues have modulus smaller than 1. So this is for each of the maps. But when you take the composition by the chain rule, you can arrive that this determinant is the product of k determinants. But because all the k determinants are smaller than 1 because are hyperbolic and locally attractor, then the global determinant is smaller than 1. And this implies that, of course, it's not possible that all the eigenvalues of this composition map have modulus bigger than 1, because in this case, you have product of all them would be bigger than 1. So this means that at least one of the eigenvalues of this matrix is smaller than 1 to get this smaller than 1 here. And then by the stable manifold theorem, you have at least one direction where you are going to, is an attractive, unstable manifold. So meaning that when you have K maps all with a local asymptotically stable fixed point, the composition map cannot have a repelling fixed point, can have an attracting fixed point or a saddle point and nothing more. So all the Parrondo paradoxes is something that happens with in small probability because you need systems that have no hyperbolic points. But now we are in the non-hyperbolic case. What can we say about this? This is the problem. So I will give now some statements. The first statement is what happens in dimension 1. In dimension 1, also you take two maps, two analytic maps in this, and having a common fixed point. Here we prove that the new fixed point for these two maps, the point is locally symptotically stable. What we prove that the point for the composition map, that is for the complete system, is either also locally symptotically stable or semi-stable, meaning for one side in attracting and for the other one repelling, but not never globally repelling in the point. Here there is not a hypothesis of hyperbolicity. This is in general, but we use these analytic maps. For instance, analytic maps and analyticity is used because if not, you can have fixed this point maybe is not isolated and you have accumulating fixed points. There are other, if you are not in the analytic world, you have many other possibilities. And also for, and what is here is interesting that if you take three or more maps, meaning period 3 in the non-autonomous discrete dynamical system, saying F1, F2, F3, then F1, F2, F3. Then it's possible to have attracting for the point for the three maps, but repelling for the composition. And this is the first case where we proved this Parrondo paradox. This was it's interesting, the surprise, and also that you need at least three. This was a surprise for us. At the beginning, we thought that it was not possible to have this because sometimes when you have something that is true for in the hyperbolic case, by some kind of density, you think that will be true always. No, this is not working at all. But it's curious because two maps are not enough, but period 3 maps, yes. So I will give an idea of the proof later. Now we go to dimension 2. In dimension 2, we prove that two maps are enough. So in dimension 2, we were able to prove that you can create two maps. You have two maps with both have a fixed point that is an attractor, and you alternate F1, F2, F1, F2, and you get that this new point, the same fixed point now is repelling. So this is our first nice result. I think this one that here two maps are not enough, but three, yes. And here that with two maps, we repeat many times the computations because we thought that we had some mistake but finally we arrived at, we checked many times, but I have to say that we check analytically because these points are repelling, but very weak repelling. So numerically, it takes some work to check this. Because you see, are very how to say, not very far to be hyperbolic. Then we wanted, of course, from this result, we construct in dimension 2. Then we thought that in dimension 3 would be very easy, also the same. But we were working some time in dimension 3, and we were not able to find this. So this is here we stop the first work with this. And this is the corollary of the other one that says that in dimension, if you take 3 maps, doesn't matter. Any dimension is good. If you take 3 maps, you can have Parrondo's paradoxes in dimensions 1, 2, 3, 4, any dimension. But for 2 maps, only taking 2 maps, meaning period 2 discrete dynamical system, we only were able to find the counterexample in dimension 2. And from the counterexample in dimension 2, of course, taking 2 and then 2 again, I have a counterexample in dimension 4 and 6 and so on. But because the problem is that we were the 3, you cannot study the 3 like 2 plus 1, because in dimension 1 you need 3 maps, so you cannot join the 2 counterexamples to have something in dimension 3. So what we did is stop here and say that the 3 will be studied later. And fortunately, at that time, I went to a meeting and I explained the result. And someone in the audience told me, and why you didn't prove the dimension 3? I said, because we didn't know how to do. And and we started this working together. And these 2 guys, Hernandez, Corbato, and Ruiz del Portal, were the ones that make the question at the meeting. But they say, they should be also true in dimension 3. Say, but I don't know how to do. So we start working. And we did this during all last year, by mail, of course. So, but this is the good thing. I was here. Yes. Here we were obsessed with computations, because we thought, you will see that to know if the point is stable or unstable, I am very used to use things like Lyapunov quantities and so on in differential equations. Here there is something equivalent in discrete dynamical systems that are the Birkhoff constant, and also something that are called the stability constants that I will introduce in some moments. But at that time, I was a person that has an analytic mind. I was thinking to compute the stability, And these 2 colleagues are topologists. They are unable to compute nothing. They only say, this is small, this is big, and you go and put this inside this one. So this was the point. So you will see that using topology is also possible to construct a a 2-dimensional example that is not based on computations, but on qualitative behavior. And using this idea, we go to dimension 3. You will see in a moment. So this is, here is the point. We will move to the world of homeomorphism because we were not able to do this in the analytic world. I am not saying that this is not possible, because taking a good normal form is also, I think it's also possible, but was not easy. So you will see now. This is this is what we proved, that there are pairs of homeomorphisms, but for um, for any m bigger, including odd and even. This is another construction, and we were here, the statement of this theorem, in other words, is Parrondo paradox arises in any dimension bigger or equal than 2 if you have a period at least 2 maps, F1, F2, F1, F2. And for dimension 1, even in the wall of homeomorphisms, you need at least 3, period 3. If with 2 maps is not enough. This is also what we did in the, and some words about this Parrondo the good thing of this construction that I will explain later is that we can go maybe I don't to enter in some details is maybe is better here. I take any number, any m, and any probability between 0 and 1, and then take 2 homeomorphisms from F0 and F1, such that the origin is fixed and globally asymptotically stable for both. And then we can prove that for almost all successions 0, 1, you can construct the orbit is repelled from the origin. Almost for all choice. Of course, not for all choice, because if you take all zeros, then you have that this map always is the map of 0. And then, of course, you have an attracting. This case, no. But this is, again, we use tools of probability that the strong law of numbers and all these things too. But the point is that you fix the probability, and then if the map is enough, the maps we will see have some regions where they are attracting the two homeomorphisms are stable. But there is some places where the map are like some regions where they are unstable, but globally they are stable. So if you increase the region where the maps through the points is time farther and farther, and then finally they enter, but they take a lot of time. So playing with this, we can adjust the example in terms of p. You give me 1p, and then I construct you 2 maps F0 with these probabilities. So this is this Parrondo paradoxes. Now I enter in, before going to the ordinary differential case, because it's a little different, I go to some proofs here. The first examples, in which are the examples, and then how we arrive to the examples. This is the first example where we found the Parrondo paradox. You have 3 maps, these 3 maps. I forgot, I decided don't tell before. It's easy to see that if the maps preserve orientation, there is no Parrondo paradox in one dimension. So these 3 maps, the fixed point is the origin, and I take the maps that reverse orientation. Okay, I have these 3 maps, and it's very easy to prove. We will see in a moment how that these 3 maps have the origin as attracting fixed point. To see this, just you need to this is a standard way, this map, to know if the origin is attracting or repelling. You compose 2 times this map, then you have a map that is preserving orientation, and then you take a look to the next term. Yeah, we will see. But these 3 maps have this behavior. The origin is an attracting point, but the composition map is this one, and it can be proved that this has the origin as a repelling. So this is the first example. I will say how we prove this, but this is the first example. And this something very funny happens, that you have these 3 maps, and you have this composition, and what happens is that the origin is attracting point for the 3 maps, is a repelling point for this order, meaning here first F1, then F2, and then F3. And of course, the order, this is cyclical order. This is order 3, 1, 2 is the same that this one, and 2, 3, 1. But if you change the order, this is the other order, first the 2, then the 1, and then the 3. Here, there is no Parrondo paradoxes. So what he's saying is that if we have three dynamics and the three have attracting behavior, the final behavior depends on the order where you put, how you put them. This also was a surprise for us. In the two-dimensional example, this is the example, just a very simple maps. Both maps have the origin. I will explain how to prove that it is an attracting fixed point, but if I make the composition, this map also from the plane into itself, the origin is a repelling fixed point. Of course, these maps are non-hyperbolic. Here, the rotation you see here, for instance, the first map is a rotation of 90 degrees, the linear part. So eigenvalues are the 4 roots of the unity. And here, this is a rotation of 2 pi over 3. So are non-modulus 1 and moreover are resonant. So this is again the theorem. This is nothing new. So how we study the stability? For instance, and now I go to the construction of the examples. The stability is very easy, but how to know in dimension 1 first. If you take a map analytic in dimension 1 and that preserves orientation, this map starts. You have the 1 here, non-hyperbolic, x goes to x plus this term. And this term gives the stability. It's clear that if this m is odd or even, you have the different situations. If this term is even, you have a semi-stable fixed point, and this m is odd, then the sign of this number gives if the origin is attracting or repelling. So these numbers sometimes are called when you have that you preserve orientation, this is one number. You write your map, make the Taylor expansion, and take a look to this number and this exponent. And if this is even or odd, and the sign of this AM gives the stability of the point. But if you have a point, this is very curious, maybe not all people is aware of this. You take a map analytic, you have the origin, a fixed point that is not preserving orientation, and you want to know if this is an attracting of a repelling fixed point, what you do is make composition of F with itself. You have this new and appears a new series. So before of the other result, you only need to study this number. If this number is the first number of these that are 0 or not 0, and if this number is the J is even or odd and all these things, it gives the result. But it's very easy that for analytic maps, only you have two possibilities. Either the map is an involution, meaning that F composed with F is the identity, meaning that the point is stable but non-attracting. This is the involution case. And in any other case, this map, the first one that appears here is an odd number, the exponent, and this gives the stability of the point. And this remains the case of the center focus problem of differential equations, where to know the stability of the point, maybe you need to go very far in the Taylor expansion of return map, but the stability of the point is hidden in the Taylor series. So like an example, look here that when I have an analytic map, and the non-hyperbolic with eigenvalue -1, if I want to know if the point is attracting or repelling, A, J are the Taylor series, I have to compute this number. If this number is different from 0, the sign gives the attracting or repelling. But if this number is 0, then I have to compute this other number. If this is not 0, I know the stability. If not, I have to compute this. If this is not is 0, this. If not, this. If not, this. And I stop it here. So there are maps that to know the stability of the origin, maybe you have to arrive to B1001, that are pages and pages of numbers. because inside the wall of analytic maps, the stability of a fixed point that is non is reversing orientation is hidden in the Taylor expansion and can be very far in the Taylor expansion. Just advance you that here we only need to have the counterexamples. We only need to arrive to B5. That we don't need to go very far. So, just to say that the stability of a fixed point is very hidden, and it's not strange that this Parrondo paradoxes happens because you need to know very far sometimes. Here for planar maps, the stability is more difficult to be computed. It's not like the first term of the Taylor expansion, but many people studying planar maps knows that to know the stability of a point is better to write the point in complex coordinates. Instead of writing x and y, I put z bar for the complex coordinates. And always, except if you have almost any point with complex eigenvalues of modulus 1 that is not resonant, you can put this in this Birkhoff normal form. This Birkhoff normal form is a form where the map in polar coordinates looks very easy because z bar is x squared plus y squared, the modulus. So the Birkhoff normal form is a way where you look very easy the stability of the fixed point. And here in the Birkhoff normal form, there are the stability. The result is that when you have a map that is enough of class at least 2m plus 2 and is not resonant, meaning that the roots are not roots of the unity of values of m smaller than this due to m plus 1, this Birkhoff stability constant gives the stability. So using this result, that for instance, here you can see if I have this map, this is a complex map. Here you have lambda, an eigenvalue with modulus 1 because I need a point that is not hyperbolic. So this is the Taylor expansion. Then this is the map. So the first Birkhoff constant is just this quantity here. Then you compute from the eigenvalue, the Taylor expansion, and depends only of the terms of order 2 and 3. We will need this. So here you see the hypothesis. If lambda cannot be a third root of the unity, because if not, this is 0. This here are the roots of the unity. This is lambda 3 minus 1. So if you have roots of the unity, you cannot arrive to the normal form. But this is the hypothesis. If you have not roots of the unity, you can compute this value, and this value is a number that gives you the stability. So using this expression, I take my two planar maps. I took two of them that this value have some sign, but when I made the composition, this changes not linearly, very complicated way, and I have three inequalities. I have the first two inequalities negative, meaning that the fixed point for the two separated maps have an attracting fixed point, and a third inequality to study the stability of the composition map. So you have to do some computations there, and here in this example, we put the simplest case. This is one of the simplest cases where appears. So from this is what we did with the analytic. This is what we did in the analytic part. I promise you something about the part, the topological part. So in the topological part, for homeomorphism, there are two parts. First, this is stronger that we did in the first result, that here that for homeomorphisms, you need also three maps. This is curious because in our first paper, I work always with Taylor expansions, and I made many computations to prove that you need at least three maps to have Parrondo paradoxes. Three maps meaning alternating three maps. But here is curious because after studying the same problem for homeomorphisms, here we have no Taylor expansions, but I don't pretend that you follow this. I even left this fixed, just only with inequalities, we arrive to the proof that even for homeomorphisms, you need at least 3 homeomorphisms alternating to have the paradoxes. And here maybe is the only thing that I will say about the new example. Maybe here is clear the idea. The idea is that this map in the radial component, just any point, what you take any initial condition, only I am looking at the angles. The angles, you start a point, then you go turning here, and you go to this direction, and at the end, the limiting of all turning points start from here and go to this one, and finally tend to this direction where you enter. And there are a region outside of this blue triangle. The points go each time far and farther. But here, any points start here, go far and in this direction, then even farther. But when you enter to this triangle, you start in this trapping region where you start to enter in this region. So the size of this, there is some expansion in this direction and some contraction in this direction. This is the map F. The map G is something similar where this blue triangle is in another direction. And so what is happening is you go many times going away from this, but when you enter here, you are lost because you enter. But on the other side, the other map is doing the same, but with another direction. So playing with these two directions, and the constants of contraction and expansion, we can manage to do this, and also to do this in average. And so doing this with averages, we go to the other result, the one that uses probabilities. So this is what I wanted to say only about this topological result. And then the good thing is that using this radius angle, we can go to more dimensions because you have radius 2 angle, radius 3 angle, radius 4 angles, and you do like some general polar coordinates in Rn, and you do this from dimension 2 to dimension 3 is very easy to go. But the dynamics have nothing to do. This dynamics here, the one that I had in the other one was related with complex rotations, and this one is even not differentiable at the origin. This is only a map that is invertible but has no linear part. So the dynamics are not, you have no clear dynamics very near the origin. This is nothing, dynamically, both have attracting fixed point, but have nothing to do. They are not conjugated, of course. And the part about differential equation, the idea is very easy. Here, I learned from these systems. I was in a jury in a PhD jury in Paris. The advisor was Jean-Pierre François, that is here, and they studied this kind of systems, studying, for instance, populations of mosquitoes and it's very. For me, the easy way is during half year you are in winter and half year you are in summer, and the model is different. This is simple, like this is the simplest point of view. And we thought maybe here also we have paradoxes, but why? Because after half year you have the map of the first system, and after second year, at this half part of the year, the other half part, you have another map, and the maps are the flows. More or less is the same. But so at this point, we arrive to the problem: is possible, given any map, that this map is the flow of time one to the good ordinary differential equation? This is the point. If you can put all this together, maybe from the discrete example, I can construct the continuous example. So the point is just a moment ago, these are the two maps that I present for the Parrondo paradoxes, this F1 and F2, are our counterexample for Parrondo paradoxes in the plane. The one done with Birkhoff constants and so on. This is the complex expression. So the point is possible to have a differential equation such that the map of this differential equation at time one, the flow map is this one, and the answer usually is no, no, because there is some not, it's not written anywhere that complicated, this is my pseudo theorem. No, it is recorded, this stop, record, no, no, there's no need to stop. You have a simple map. This is not the flow of a differential equation. Unless that differential equation is very complicated. And if the map is complicated, then you can have a simple differential equation. So that there is not possible, both things seem simple. The map here, the map is very simple. So the differential equation is not polynomial, of course. Except very few cases, this is like a rule. So what we wanted, not given this map, to have a differential equation that has this as a flow, time one, but with some some mistake here, that this one here, sorry, I am sorry, I put here the theorem. No, here, take a simple map, this one. If this omega is not a cubic root of the unity, there exists a unique vector field satisfying that the flow time one is this map plus something more. This is what we need to do. Because the proof is given the map, that is the one that was the counterexample for the discrete case, I construct a differential equation such that the flow is this map plus something more, but higher order. So putting all this together, sorry, here, I take the two maps that gives the Parrondo paradoxes. Then I construct the vector fields that such that the flow of time one are almost the maps, but with some odd or big O times after. Then when I change from one vector field to the other, what I am doing is the flow of this differential equation is during one unity of time you go by vector field one, and the other unity of time you go by the vector field two. But then each time this map, you have some mistake that is this big O. But finally, putting all together, that the flow of this map that first goes one flow and then the other one is the one that the composition of the two maps some plus some big O, because the Birkhoff constant are hidden also in the Taylor's expansion until order 3. This doesn't changes the stability. So if I have two maps that give a counterexample and for which the stability is given in the Taylor series until order 3, this map, you can have a counterexample for the differential equation simply taking these vector fields that have only this Taylor expansion for the maps. I think that I have more or less explained it. And just for instance, just to give an example that this is not always true, but almost. Here, I show you one map, this one, that has no vector field. So it's not so easy. The theorem is that almost for all map that you invent, that of course has to preserve orientation and so on, and this to be invertible, almost any map is almost the flow of time one, but not always. For instance, this concrete map, there is no vector field such that when you do the flow of time one, you have this map as some order 3 terms. So this makes not the trivials. You have to make computations to be sure that you can, from the maps, have the vector field. And so with this, in this talk, I have seen that this Parrondo paradoxes appears in many situations, and this is all what I wanted to explain. Thank you for your time.
Okay, thanks so much for your talk, Armengol. I think this is a very interesting topic because we are used to see models in which parameters change in time, but here you are changing the model, and I think this is really powerful. Okay, so we have a question. I think that it's better, Tomás Lázaro, if you can turn your microphone on and do the question. Make the question. Yeah.
I do. Thank you very much, Josep. Okay, thank you very much, Armando. Very fascinating talk. I have a question that could be very, very naive, but assume that, for instance, you are in dimension at least 2, and then you provide a word. The word is composed by symbols which are R or L, depending in the fixed common point is repeller or is locally asymptotically stable. Can we find a sequence of functions in such a way that their combination always provide the word you want? It could be finite or infinite. I don't know if I'm expressing myself. So just the concept, select the word.
You want to put a sequence stable, and stable, and stable.
Yeah, for instance, yeah.
And then you put, you have 2 maps only, or how many maps?
I don't know, that's my question. So could you reproduce this symbolic dynamics just with a given number of maps?
Oh, but this is something to start thinking from now, let's say from 0. I don't know if someone has studied this point of view. In fact, this Parrondo Paradoxes, when we tried to publish this, some referee was against to use the Parrondo name here because say this is not Parrondo because Parrondo is another setting. Here you study stability, but this is a problem that we don't found this at the very beginning. We start thinking not about a point. We thought about you have 2 dynamical systems, F and G, and you understand very well, and you want to know what happens if you alternate them, only this. But at some moment, we start fixing and we say, we don't understand, we arrive to a point. And at that moment, we thought that for a point should be very trivial problem, and we arrived to something that was shocking for us. This paradox thought that you don't know nothing about this, and someone said you prove that for hyperbolic case you don't have paradox, so you don't expect this. This is the reason we put the paradox. And the name just is because, but now you are starting with a different problem. You give me a list of stabilities, and you want to know if it's possible to realize with a finite number of maps.
Yes.
Interesting. I only can say interesting, but no idea at all.
Okay.
Because we start at the very beginning with high expectative what we can do, and we start with only 1 point and with a paradox that we didn't expect. So I cannot say nothing about your question because most probably would be another paradox.
Probably yes. Okay. In any case, thank you very much for your nice talk, Armengol. Thank you.
Thank you. Thank you.
Okay. Thanks, Tomás. Any other talk? Sorry, question.
I want to give a second talk. Thank you.
Okay, you're welcome. Okay, so yeah, let's thank also again Armengol for this amazing talk. Thanks so much. Now we will move to the second speaker. Second speaker is Blai Vidiella. Blai has recently joined the Central Recerca Matemàtica. He will talk about his research that has been mainly developed at Universitat Pompeu Fabra and the Institute of Evolutionary Biology. His research interests are theoretical ecology, dynamical systems as well, and he's also working in systems and in the wet lab doing synthetic biology. And he will talk us about can ecosystems live in a ghost state. Thanks, Blai. You can start whenever you want.
Perfect. Do you listen to me?
Yes.
Okay, perfect. Thanks first to the organizers for giving me the opportunity to give this talk here. And first, also thank my co-authors that without them, the works that today I will expose will not be possible to be done. Nowadays, we are living in the Holocene. This is a strange period in the geology of our planet, because since 10,000 years ago, we are living in a more or less stable planet where we have constant, more or less, temperature between +1 and -1 degrees of variation in these 10,000 years. And the civilization only knows this because the beginning of the agriculture is already in this geological epoch. And we are all coexisting with these beautiful ecosystems that we usually think about, the savanna, the ecosystems from the rainforest, or even the poles with the ice. But nowadays, this is not longer the case. We have degraded them. For instance, we are bleaching the coral ecosystem, and the desertification is advancing, and we have deforested a large part of our wild ecosystems. This is because a constant increase in the demands of our society. We have been exponentially growing as a population size, and these have released loads and loads of CO2. As you can see, more CO2 than never have been recorded in our atmosphere. And this is also driving our temperature to rise. Moreover, we are extremely good in doing engineering, and we have achieved the possibility of doing very, very persistent objects like the plastics that nowadays are a pollution for the ecosystems because they cannot manage to degrade them, at least in an efficient way. And when the plastic is interacting with the communities in these ecosystems, sometimes the plastic is accumulated and sometimes it's almost constant. And this maybe it's indicating us that this plastic is entering in the trophic chains, and as top predators, we are eating plastic molecules that it's not a good situation for us. This increase in the pollution, let's say, and driving ecosystems to their limits have given us the opportunity, or may say the worst part of all this, it's that as humans, as societies, we have the power to change the complete planet, even in a higher and more efficient way than the geologist process that have driven our planet for the last almost 1 million years or so. And as humans and human societies are pushing the ecosystems from many different ways, for instance, degrading them or depleting them from species. And we are releasing some chemicals that they are already present in these ecosystems, like phosphorus and nitrogen, but we are releasing more than the previously concentrations. And sometimes this is toxic, and sometimes they change the composition of the ecosystem. And we are reaching some critical points of these ecosystems that could give to the planet, or could change the planet in a critical way, not smoothly. We probably from 1 year to another observe big changes to the ecosystems, and maybe to the complete Earth planet. These are the identified, let's say, tipping points of the planet. One is really easy to understand. We have warmed up our planet to the point that it's almost impossible to sustain Greenland ice. And this means that there's lots and lots of water that will be released in the ocean. And this will drive and slow down of the ocean currents, and this will affect the climate of all the planet, probably pushing more and more ecosystems to cross their own tipping points. This has been observed in many ecosystems where we have two stable states. For mathematicians, this is easy to understand. This is a B-stability region, and some perturbations, for instance, in the parameters, could drive the ecosystem to a degraded state. But also, this can happen if we change the initial condition, the amount of this species, and providing them going to the extinction state, this degraded one. One ecosystem where this happens are the semi-arid ecosystems. The semi-arid ecosystems nowadays cover about the 40% of the planet, and more or less a third of the global population is living there. This means that they are really, really important in terms of the magnitude of the problem. And moreover, they will increase because the semi-arid ecosystems are those ecosystems where there's lack of water. And as we are warming up the planet, or the planet is warming up by itself, and these ecosystems or more ecosystems will have this particular case that they lack water. The water evaporated and needed to sustain the vegetation, it's greater than the rain or the water that is released in these geographical regions. And in time, are the expected values that we can reach in area of the planet. Maybe it's almost the 60% when in less than 80 years. These ecosystems have have the peculiarity that can give us the option to see them how they change, because of the lack of water, they are self-organizing and have self-organization patterns like these spots, and sometimes they go from spots to stripes, and we can eventually even see deserts where they should be vegetation. And these two images are from different parts of the planet. Namibia and Australia are quite far one from the other, and they appeared more or less in the same years. This is one of our biggest case studies, and we study this B-stability. This is from Verdugo and Fernando Maestre Nature, Ecology and Evolution, where from real data, they show that there exists this B-stability. For the same value of aridity, there are different ecosystems that can be present there. And this can also be seen from the satellite images in the border between Egypt and Israel, where Egypt have a desert state and Israel have vegetation. And this is only because a difference in their policies about the letting grazing or not for giving food to the society. When this vegetation, the vegetation that live here, these areas disappear, the sun can mobilize, and then we have this sun dust and sun clouds that give really bad times. And this is the US in the past. This have happened because of the agricultural management of some landscapes. And this is a prediction that says that all this gray part of Africa are frozen dunes that can be mobilized when this vegetation disappears. And are millions and millions of people that could not live in their own homes. And we will have a really big problem, sociopolitical problem, because they cannot continue in their lands. No? This change between vegetated and desert states have already passed in the past. And the Sahara nowadays desert was green. There were vegetation, and in terms of 1,000 years, as it can be seen here, and this vegetation disappears, and the complete landscape becomes the desert that nowadays we know. This can be speculated or not, but this seems that it's not because of a change in the insulation. Maybe it's for a change in another peculiarity, or it can be that the system was really close to the tipping point, and once the tipping point is crossed, you have this ghost dynamics that Thomas have talked previously, and many other talks like Luis have said, that near to the tipping point, we have this ghost phenomena where the vegetation, in our case, can be maintained in the ecosystem, but given that the ecosystem have crossed this tipping point, they will eventually become extinct. This means that maybe the current vegetation in these systems, it's not the stable state. It can be the ghost of the past. They could be living because before there were vegetation, but the current situation and the current conditions, for instance, in temperature or in soil degradation, are not able to sustain this vegetation anymore. This is a saddle node bifurcation, and for the reason we have this 1/2 tendency. If you are far from the tipping point, this is the right-hand side, the time to extinction becomes more and more frequent, and this is what is shown here. In this peculiar ecosystem, we thought that we can sustain the population of, well, the vegetation fraction above this ghost and take profit of this, doing some replantations. If when the ecosystem is going down to extinction, we perform a small perturbation, a small replantation, we will achieve the possibility of having this ecosystem be maintained in the coast region, the region where previously there were this stable state. And this also can be seen in when we add noise to our simulations. This seems to be a good situation. If we only take into account that this is a saddle node bifurcation, maybe if we take into account other conditions, this can be changed in the ecological field. No? Another place where we are changing the things is in the trophic chains. We are top predators because we eat almost anything that we can. And these are the structure or the network that have been established by Elton in almost 100 years ago. And these are many species interacting between them. Some of these species, like the top predators, are key because when there's a lack of these predators, we can observe changes in the complete ecosystem, from having or to not having these species. This is also illustrating us that more or less these predators are maintaining like the system in one of the stable states of the ecosystem, and when they are not present, the system goes to a degraded state or a different state that usually have less complexity. The lack of complexity, as it is illustrated in this article, it's bad because species are like a storage of many molecules. For instance, the carbon that nowadays it's being released in the atmosphere in high quantities because of human interventions, it's stored in the organisms that live in these ecosystems. For this reason, a degraded state where we don't have this, in this case, I think that it's the otter, become a ecosystem that it's not able to sustain the same amount of carbon. This means more carbon being released in the atmosphere. In this article that hopefully in the near future will be published, we have analyzed a small chain of species, a predator, a herbivore, and the vegetation, how they interact between them. And we have identified that even in the smallest case where we have a herbivore and the vegetation interacting between them, we can have trajectories in the parameter space. This is the degradation of the habitat, like pollutants or deforestation or high rates of degradation. This is the mortality of the vegetation, and this is the efficiency of hunting. If we observe this trajectory, this P trajectory, we observe that there are many changes in this system. We start from a system that is unable to be sustained. We have a heteroclinic bifurcation, where from not having anything, we start to have oscillations in the population. Afterwards, we have a hub bifurcation. These oscillations die, or let's say they became damped oscillations. Afterwards, we have a transcritica. These transcritica have what for the ecologist it's really important. This is the critical slowing down. And afterwards, we have a saddle node where the vegetation dies and disappears. In all these different bifurcations or transitions, depending on the vocabulary we are using, we have studied their transients. This for all these panels, we have studied only with the soil degradation or the degradation of the habitat. And we have this, that Hopf, Andronov, and transcritical bifurcations have the same behavior, this -1 exponent. The saddle node, it's a half, as we have were previously exploring in the other work. And we have the heteroclinic that maybe this needs more studies, but it's the first time, at least to our knowledge, that this is studied in the ecological systems. And they have not a straight line. They have like jumps in these transient times. These are really important because there are policies that, for instance, allow to fishing in some areas, and when they remove the ban, there's a time transient, but the captures, the amount of fish that it's captured, becomes to 0. This means that the fishes have almost extinct in this region because of the possibility of being fishing in this place. Moreover, this diversity of transitions, maybe it's really important in ecology. And here there's this work from Verdugo and Maestre and Ricard from the last year, where they show that in aridity, in the arid ecosystems, there are multiple tipping points, and maybe they are not all from the same kind, the same saddle node bifurcation. And in our work, we have shown that there can exist even a concatenation of these transients. And this is a situation where we have the saddle node transient, the cost, and afterwards we have this transient dynamics of huge oscillations that came from the heteroclinic bifurcation that I have shown previously. In ecology, as Luis have shown in the morning, there are also these kind of transients in discrete time series. Here we can see. This is really important because close initial conditions could have extremely different large periods before having the complete extinction of the ecosystem. And this is really important, at least for me, when we are talking about the ecosystems. And nowadays we are even exploring this in a different system where we have a cooperator and a strict parasite. And we are looking, well, we have found that there are these scaling laws of -1 also in the normally hyperbolic invariant manifolds. This, for me, it's really extremely important because it's giving us the idea that maybe the ecosystems that we are seeing nowadays are the ghost of the past. They are the ghost of the previously stable states, but nowadays they are endangered enough to have these rapid changes in the dynamics and become extinct. There are different ways of managing these dynamics and these ecosystems. For instance, one of the more beautiful for me, it's the rewilding idea, where some predators, for instance, or some species, key species that have been removed, for instance, by hunting of some ecosystems, we can release again. For instance, the more paradigmatic example, it's the wolves in Yellowstone. And then we can observe that there is a complete change in the ecosystem. The release of wolves have changed even the river, because beavers have arrived to Yellowstone and they construct their dikes and they are changing the river course. They have also induced the invasion of bears, and they have increased the height of the vegetation. Here you can have the number of seeds of cotton, the beaver amount since the introduction of the wolves. This is the dynamics of the intrinsic dynamics of the wolves. The bisons, they have recruited lots and lots of species in detriment of the elks that were overpopulating this ecosystem before. And here you can see images from the real field where there are changes in the landfill. In my thesis, the idea that we have been also exploring is to manage these ecosystems as ecosystems that are becoming inhabitable. And what we have done, or we are thinking, it's about terraforming them. This is like a science fiction idea, because terraforming means to make similar to Earth, for instance, a planet like Mars. But our sentiment is that nowadays planetary ecosystems are becoming inhabitable. There are massive extinctions, and they are unable to sustain the same biodiversity that previously was present. And for this reason, we want to make them habitable again. And our idea is to use synthetic biology to do so. This is a strategy that have been studied by Complex System Lab, led by Ricard Solé. And we have the idea of having, for instance, microorganisms that already live in these ecosystems, engineer them, for instance, making them able to produce more a molecule that was already present, or able to degrade some chemical that previously they were unable. and try to see how this small change in this organism can be propagated to the complete ecosystem, making this ecosystem more sustainable or able to sustain more life than previously. And these are some examples. And in this paper, what we hypothesize is that maybe we can structure the interactions between this synthetic organism and the ecosystem in 4 different manners. Here, the synthetic organism maybe it's able to retain water. This is good for the semi-arid ecosystems. And this water increase the probability of growing vegetation or other different functions like function and die, where there is, for instance, a release of oil or plastic, and the synthetic organism is able to degrade it. And we have computed what happens. In many of the cases, what we have found is that in these simple models, it's that this could be a good idea. Maybe we can change the ecosystems from a degraded state to a more diverse state by the introduction of these species that can make huge changes in this environment of these ecosystems. This could seem like science fiction, like I was saying before, but we have already done this in the past. Charles Darwin found the Ascension Island in their trip with Beagle, where there was a army station there, but there were no vegetation. They describe it like a mount of cinder because this was a volcano that was completely desert. But when Darwin and Hooke talk with the Queen's Garden, they achieved the possibility of releasing lots and lots of different species of plants from all over the world in this small island that is isolated from all other countries. And nowadays, what we can observe is this one and this one. The previously uninhabited landscape, nowadays it's green and it's full of life, as we can see. And the measures say us that this is a mature ecosystem. From nothing, we have changed Iceland from being a mount of cinder to be a green place able to sustain life. And this is the other message from the talk, giving us, if we have been able to do that in the past, maybe we can try to do it now in a more large manner. These are the works that I have presented here. These 4 are about this transient dynamics, and these are the more terraformation ones. And finally, thanks to all my collaborators to give me the opportunity to do all this stuff. And thanks to everyone for listening.
Okay, Blai, thanks so much for this very nice presentation with a lot of nice images and I think important messages. Okay, so we have a long comment from Javier Gamarra. Let me read it. So he says, just days ago, officially, the UN Decade on Ecosystem Restoration was inaugurated. However, I am aware of projects that, while especially explicit in detail and considering social safeguards and constraints, they tend to find priority restoration areas based on classic linear optimization approaches. Then he asks, what are the dangers of ignoring these nonlinearities here, and what basic messages would you send when searching for priority areas in restoration?
Well, thanks, Gamara, for the question. I think that this is fundamental. In fact, I think that we have learned from these models that nonlinearities are extremely important. And for instance, there are works where we can simulate the dynamics of an ecosystem using, for instance, a cellular automata or things like that, and that have shown the depending on the area degraded and how this is distributed over the simulation area, it's crucial to see if there's a change towards an extinction of the complete population, if there's a decrease in the biodiversity of this simulation, or they are able to maintain the same. No? I think that there are many works in theoretical works that are pointing towards this idea that nonlinearities are fundamental in ecology. They rise from each interaction between a species, between individuals, and between the individuals and the environment. It's all interconnected, and by definition, this gives us the idea that there are nonlinearities playing a huge or a key role in the ecosystems. Maybe a naive idea is to protect a bigger area than small areas that are disconnected between them. But I don't know. We should study this further in the future.
Okay, so Javier, if you want to add something, you can turn your micro on.
Yeah,
If you want to,
of course.
Okay.
Oh, no. I will look for the next question. Thank you very much, Lai.
Thanks, Javier.
Okay. So, yeah, we have another question by Sonia Kefi. He's thanking for your really nice talk, as you can see. So, yeah, this is a good question. Do you see any way ghost states could be identified in ecosystem data? Do they have some kind of signature?
Well, I think that this is a big question, as Sonia and Josep may know, but I think that we should study the dynamics of the warning signals near these fixed points as we have done in other works, but I don't know. They should behave like slightly the same than before the transition, and this give us the idea that maybe we can know it when we see the extinction and that they were in the ghost. But nowadays, I think that we need more theoretical studies in order to see what happens in this ghost. Maybe these ideas of doing the simulations with noise and doing these huge mathematical efforts that some of the talks have shown can give us the idea on how we can measure this in ecological data. I don't know. But thanks, Sonia.
Okay, so another question by Josep. So he says, nice talk. You showed that transients close to critical transitions follow power laws.
Yep.
How do these transients change when you consider spatial effects? Are they similar than in the simplified mean field models? Or in other words, does the spatial explicit dependence have any effect on these transients?
Yeah, in fact, I'm not an expert. I have not studied this, but Josep have done. And in their works, they see that this space increase these transient times, and depending on how the space implementation is done, even the transition change, and this is really important. Maybe Josep can add something here.
Yeah, yes. So typically people working in theoretical ecology, well, we know from many years ago that usually space make transients longer. So the role of these transients length in the scaling has not been very deeply explored. And in my talk tomorrow, I will give some insights on these effects, because when one takes into account space, usually there are a lot of surprises, okay? Because you have processes of spatial self-organization, and actually it can modify a lot the, even if the scaling appears, but as I will explain in my talk, even the transition can change. So you can have a kind of catastrophic transition, and then the transition can become smooth. Okay. So we have another question by Patrick Govoni. Great talk. Okay. From what I could see, the first bifurcation on the two-species system on its way to extinction, heterotrophic, I believe, I think it means heteroclinic, was exhibited by growing oscillations. Have you looked into perturbing the system at the peaks of the oscillations to restabilize? That is in a similar way that you looked into stabilizing a ghost state system.
Okay, I haven't get it. You want to destabilize or to stabilize? Have you doing the system?
To restabilize.
Yeah, to restabilize. Right.
Okay. Yes, in fact, in the article we show the phase portrait. I think that I haven't had here in the slides, but what we see is that any perturbation that decrease this peak will lead to a recovery of these dynamics. We can maintain these populations in these oscillatory dynamics by decreasing, for instance, the herbivore amount when they are in the highest peak. But these have not been extensively explored, but this can be shown graphically because the heteroclinic bifurcation give these huge oscillations on the species that if they are smaller, they are inside these transient dynamics. If we increase, for instance, the amount of herbivores in the ecosystem, we will cross the boundary and the ecosystem will rapidly go to extinction without exhibiting these transient oscillations. You can turn on the micro if you want.
Yeah.
Okay, so yeah, I don't fully understand the system, so it might be naive, my question. But
no.
Just looking at the system from like a kind of a process control point of view. On the left, like the top left part of the heteroclinic box has this like increase in oscillation sort of behavior, and I was wondering like maybe is there a way to restabilize before it kind of the system goes into the point of instability that it's is there a way to basically I guess deduce the dynamics and then figure out how to balance such that you retrieve the initial flat line there?
Okay. You want to recover the flat line. This is really in the parameter space. The dynamics of being in the straight line and the dynamics of being or becoming extinct doing these oscillations are really far, because we are talking that the Hopf bifurcation, the bifurcation that enables you to have a stable fixed point, a stable condition, not oscillating, it's here. And the heteroclinic bifurcation, the bifurcation that give these oscillations, the birth of the oscillations that will die with the Hopf bifurcation, it's here. Parametrically are really far. Maybe we can have a strong control on the amount of each species, or maybe a strong control of how the vegetation it's being growing. But I think that these they are too far from the parameter point of view to achieve this idea of before going to extinction in an oscillative manner to go to a stable point. They are really, really far. And having oscillations is not bad. They are all over the data sets, the ecological data sets. But what it's what it's bad is to go to extinction and without knowing. No?
Right, okay. Okay, yeah, thanks.
You're welcome.
Okay, just let me add that, yeah, this is control theory is a very interesting subject, and especially with this kind of bifurcation. So perhaps, Patrick, we can contact by email and discuss this a little bit more if you find it okay. Okay.
Yeah, I would love that.
So yeah, okay, thanks. So thanks, Blai, for your amazing talk. We now move to the last speaker of today's session about bifurcations and chaos. So the next speaker is Gemma Huguet. She's a researcher at Universitat Politècnica de Catalunya. She belongs to the Dynamical systems group there. And her areas of expertise are dynamical systems. She's using dynamical systems theory specifically to neuroscience. She is also doing research in oscillators, phase response curves. And today she will give a talk with title Quasi-periodic perturbations of heteroclinic attractor networks in models of bistable perception. So Gemma, when you want, you can start.
Thank you very
Thanks so much.
Thank you very much, Josep. I understand that you all hear me. So I'd like to start by thanking for the invitation to this nice conference. I'm very happy to contribute to this conference. So what I'm going to talk about is joint work with Amadeu dels Ams and Antoni Guillamón at UPC. And it's about heteroclinic attractor networks, and in particular, an application to a problem in neuroscience. But I think that the topic might extend also, or might be of interest also to other areas that have appeared in this in the talks in this conference, like ecology or population dynamics. So the motivation for this study is the fact that oscillations are ubiquitous in the brain, in the sense that we find oscillations at very different levels. At the single cell level, that is at the neurons show oscillatory behavior, but also at the population activity level, that is the activity of a group of neurons shows macroscopic oscillations, and also at the level of brain areas. But these oscillations that here are plotted like very smooth and regular and nice, actually in real applications or in experimental data, they have a very irregular behavior, or like some of the rhythms do not have these nice regular patterns. So this is, for instance, an example of the so-called up and down states studied in neuroscience, where we have that neurons or groups of neurons show an activity pattern or a rhythm of its macroscopic activity that has states of high activity followed by states of very, very low activity. And this rhythm of like up states and down states, as you can see here, is pretty irregular. Other examples where we have these irregular rhythms are in the problems of, or like in the perceptual multistability experiments. Perceptual multistability occurs when a subject looks at a visual percept that is ambiguous, in the sense that it admits different interpretations. So for instance, one of the classical ones that maybe you have seen previously is the Necker cube, where you can see either this face closer to you, or either this face here closer to you. And actually, when subjects observe this type of stimulus, the perception actually switches over time. And this switching is inevitable and it has some random component or irregular dynamics. Other examples or similar examples in which you observe this irregular pattern of transition between different perceptions is in binocular rivalry. Binocular rivalry is the phenomenon that occurs when we present a different visual stimulus to each eye. For instance, this is a subject for which the left eye sees this type of pattern, while the right eye sees this other type of pattern. So what happens in our brain is that the brain doesn't mix the percepts, but actually the perception switches between both. And actually, when we report the alternations in the perception, we see this type of, again, these irregular patterns. So switches occur, they are inevitable in the sense that when subjects look this for an extended time, at some point our brain switches perception. But actually, the time each percept is perceived or is created is not a fixed amount of time, but it has some this sort of irregular behavior. This has correlations in the brain activity. So what happens in our brain when we are looking at a stimulus of this type is that we have that groups of neurons in the visual cortex, which is the area of the brain that encodes the information that is processed through the visual, through the eyes. And so neurons in this, in the higher areas of the visual cortex, they show correlates with perception. What does it mean? It means that if we record the activity of these neurons or groups of neurons while the subject is looking at this type of stimulus, what happens is that we see neurons that they are highly active, they show high levels of activity when the subject is perceiving, let's say, percept red, while their activity decreases or has low values when the subject is perceiving the opposite one. And they activate again when the subject perceives their preferred percept. So basically, what we have is these alternations in the neuronal activity of the populations in the brain that have these rhythmic patterns, but these rhythms are irregular. Actually, when we put the distribution of times, when we plot the distribution of times, these actually typically follow what is called a log normal distribution or gamma distribution, which basically means that if we take the logarithm of this random variable, it's normally distributed. The classical models to study this type of phenomenon or this type of rhythms in the brain are the firing rate models, which basically describe by means of a system of differential equations the activity of two different populations. So R1 encodes the activity of population 1 and R2 encodes or models the activity of population 2. These two populations are correlated with perception in the sense that when the activity of population 1 is active, it means that we are perceiving percept A, let's call it. And when the activity of population 2 is high, it means that the subject is perceiving percept B or percept number 2. So these systems of equations that describe the activity of these neural populations are modeled using this classical system of equations known as the Wilson-Cohen equation. And basically its activity is a function of the total input that this population receives. And the total input that this population receives is an external input that we may think that the input that is generated by the external visual stimulus, okay, that we may think that is the same for both populations because there is no bias towards, so for this setting, there is no bias towards one percept or the other, and we think that they are both equally possible. But they have self-excitation, but interestingly, or like more remarkably, it's important that these populations inhibit each other. So that when population 1 is active, it sends inhibition to the other population. Moreover, in these systems, there is what it's called adaptation. This is a slow process that takes place in these neural populations that whenever they become active, after a while, they fatigue of this high activity state, and this slow negative, and they send to themselves this slow negative feedback that after a while produces that the activity of these populations decreases. But in these models, apart from this adaptation and from these components that I explained, they also add noise, because they use noise to explain or to model the irregular behavior or the irregular patterns observed in the experiments. So the way they work, these models in the mechanistic setting, and this is using this hypothetical energy function, is that when we consider this system of two populations with adaptation, what we have is that in the initial setting, we have this double well potential where we have two attractors. The system is bistable, which actually correspond, and there is this saddle point in the middle that determines the basing of attraction of each attractor. So what happens is that we set the system at an initial state where one population is active while the other one has low activity. And then adaptation has the effect of like just reducing the depth of this well, and up to some point, this attractor here disappear actually via saddle node bifurcation, and the other attractor in the system is the other equilibrium point. So the trajectory approaches the other state, and then what we have is now that the other population is active while the previous one is suppressed, and this produces alternations. Another way to produce alternations is to assume that there is no slow negative feedback, there is no adaptation in the system, and transitions are only driven by noise. So the system is set in this regime with this double well potential, and then noise produces switches between the two attractors. And the other possibility is to have a combination of both, in the sense that we have weak adaptation, in the sense that the adaptation is not capable by itself to produce, to cause this attractor to disappear, but it reduces the depth of the well, in the sense that then when we apply noise, this noise can switch to the other well much easily. What happens is that in the setting with only adaptation, what we get is regular oscillations. And this is not what the experimental data shows. If we, in the setting of only noise, so here the colors, sorry that I didn't say this, represent the variables R1 and R2, that is the activity of population 1 and the activity of population 2. You can see transitions that whenever population 1, for instance, the red is active, it's close to 1, population 2 is suppressed, it's close to 0, and then they alternate, okay? So this is with only adaptation, but then we get regular dynamics. This is with only noise, but then what happens is that I didn't put it here, but the distribution of times, in this case, it's an exponential. So it doesn't fit the experimental data. But noise with weak adaptation, so a combination of both, generates these irregular oscillations, while at the same time, it reproduces these gamma distributions that I showed you before. The thing is that in these models, the key element to produce the transitions the key element to produce irregular rhythms is to add noise. And there are other models that we want to explore and that I want to talk about in this talk, or is this winnerless competition models. So these are models that based on, or that they contain what it's called heteroclinic attractor networks. So what is an heteroclinic attractor networks? This is a chain consisting of saddle points connected with heteroclinic trajectories. An heteroclinic trajectory is an orbit that in infinite time travels from the from minus infinite time, in minus infinite time approaches one of the saddles, and in time plus infinite approaches the other saddle point. Okay, so combining saddle points and heteroclinic orbits, this creates what it's called an attractor network. And this an heteroclinic attractor network, and they are attractor because they attract trajectories nearby. What happens when we consider an initial condition and we integrate a system that has an heteroclinic attractor network? So what happens is that, as I said, these heteroclinic attractor networks attract trajectories nearby, and we go, if we look at the coordinate P, where we have a saddle point at P equal to 1 and another saddle point at P equal to -1, we start close to P, to the saddle point that has coordinate P equal to -1. And then, since there is this heteroclinic orbit here, what happens is that the trajectory escapes from the vicinity of P equal to -1 and very close to this heteroclinic orbit, and approaches the vicinity of P equal to 1. It stays close to this saddle point for a while, and then escapes through this direction where we have this heteroclinic orbit that brings us back again close to the vicinity of P equal to -1. What happens is that since this is an attractor, every time we get closer and closer to the saddle point. So the time we spend close to the vicinity of the saddle is longer. So now we spend longer time close to the vicinity of the saddle, and we escape again through the heteroclinic network that connects with P equal to 1. Here you can have the time evolution of the variable P. So we start close to P equal to -1. This is a very fast transition close to P equal to 1. We stay here for a while, then we transition fast back again to P equal to -1. Then we stay close to P equal to -1 and then transition again. And the time we spend close to the vicinity of the saddle is longer and longer. When this is what happens when we don't put any perturbation in the systems. When we add a noise perturbation, so we add this noise term here, what happens is that what it does, it shortens the time we spend close to the vicinity of the saddle points, and then we again move back and forth between the vicinity of P equal to 1 and P equal to -1, but these transitions, as you can see, are faster. Again, this is with noise. So what we wanted to explore is like, can we reproduce the same dynamics, but instead of using noise, using that actually with noise, sorry, I forgot to say this, the distribution of times that we spend close to P equal to 1 or P equal to -1 now resembles this log normal distribution that I showed you before for the experiments. So going back to my point is like, can we reproduce the same dynamics, but instead of using noise, using a deterministic function, which is a quasi-periodic perturbation. And a quasi-periodic function consists of the sum of periodic functions with frequencies that are non-resonant. That is, they don't have a rational relationship. So in this case, so here I'm already telling what's going to happen is that if we simulate this system, but instead of noise, we use a quasi-periodic perturbation, what we can see is that we can produce transitions between 1 and -1, also in a similar way as noise. And actually, when we plot the distribution of times, we get this typical log normal shape. What I'd like to show you that it is, so what we want to do is to study in more detail the dynamics that emerges in these systems with this quasi-periodic perturbation. And for this, we are going to use the separatrix map. which has been used in the dynamical systems field, introduced by Shilnikov, and then has used by many authors in the literature in dynamical systems. So we're going to construct a map close to this heteroclinic cycle that describes the dynamics close to this heteroclinic cycle. And the way we're going to construct this map is going to be like sort of semi-analytical, in the sense that this is an approximation of the dynamics close to the heteroclinic network by means of analytical tools. Why we want to do this? What is the motivation for this? Well, noise actually encodes all those elements in the biology that we don't know exactly what are the sources of it, and also basically noise is sort of introduced in these systems because we want to reproduce the irregular behavior. But then when we want to ask like what this noise represents, so sometimes it's hard not to say exactly what this noise is modeling. So I mean, motivated by this question of like, what is the level of complexity of the inputs that we need to put in order to get these distributions? So we wanted to explore this question of a quasi-periodic perturbation. Basically, this is what we want to do, is like, what happens if the inputs that these networks or that these populations are receiving, they come only from a few sources. And we explore first this idea with the benchmark model, which is the Duffing equations that I'm not going to discuss here, but they are in this paper that we published in Chaos. And then we moved to study heteroclinic attractor networks for a model of binocular rivalry, which is the phenomenon that I explained you before. The model that I'm going to consider is this three-dimensional model where we have three variables. The variable X encodes the activity associated with a stimulus to the left eye. Y encodes the activity associated to the stimulus to the right eye. And P is a sort of an arbitration variable. Basically, P is going to move, as I showed you before, between 1 and -1. And it means that when we're close to P equal to 1, it means that the left eye is dominant, and when we are close to P equal to -1 means that the right eye is dominant. Okay, so this model was introduced by Peter Ashwin and Labrick in 2010, and what they used, again, this is a model that is the same as I showed you before. It has two saddle points here, and it has an unstable point here at the origin, which is a neutral point. And this model was introduced to reproduce these experiments of binocular rivalry, and it was simulated with noise. And the goal was to study this model, but instead of using noise, putting a quasi-periodic perturbation, okay? So again, you can see that this is a sum of periodic functions. This is expressed introducing this variable theta, which is a sort of phase that evolves with a certain frequency, omega. As I said, these saddle points have an invariant, have a one-dimensional unstable manifold that connects actually the points -1 and 1 on the plane. So this point here has this one-dimensional unstable manifold that connects these 2 points on the plane y equal to 0. And then there is this one-dimensional unstable manifold that connects the point, this heteroclinic connection that connects the point with coordinate p equal to 1, with the point with p equal to -1 on the plane x equal to 0, okay? And in the other directions, they are stable. They have stable directions. So the other directions are stable, sorry. Okay, so how do we study the dynamics using this separatrix map that I explained? So the first, what we do is like in the vicinity of these saddle points, we put sections like Poincaré sections, which are two-dimensional sections at a certain distance of the saddle point that cross these heteroclinic connections, these are heteroclinic orbits, okay? This in blue is the J in section, so that orbits arrive at the vicinity of the point with p equal to -1 through this section, and they escape the vicinity of the point p equal to -1 through this section at J out, okay? Which is set at a fixed value x equal to x star, and similarly for the point p with coordinate p equal to 1. Okay, so this is a zoom of this local view. What we're gonna do is that we're gonna construct a map, okay, that describes the dynamics from one of these sections to itself, but combining the global dynamics and the local dynamics, okay? So we're gonna consider the extended sections because actually when we add the quasi-periodic perturbation, we need to add the phases, okay? So we add the phases corresponding to this values theta. And then we're gonna construct a global map that describes the dynamics from this section J out plus, close to the vicinity of the point p equal to 1, to the section J in, or the extended section are associated to J in. And then we're gonna have a local map that describes the dynamics from this section, the blue section, to the red one. Then we're going to have another global map that describes the dynamics from this section J out minus to this section J in plus. And also finally, a local map that describes the dynamics from this section J in plus to this J out plus, okay? Combining these four maps, this describes, this is the separatrix map that describes the dynamics from the section J out plus to itself, okay? So how do we describe the local dynamics? Well, basically for the local map, it's very easy to obtain an analytical expression because we linearize the system around the equilibrium and we use the linear system. And the dynamics is very easy to express. Actually notice that this involves the eigenvalues of the saddle point, okay? So this is how we describe the dynamics of the local maps. What about the global maps? Well, for the global maps, what we want to do is an approximation of the dynamics in first order. So what we use variational equations. We describe as the dynamics which provide information up to first order of the dynamics for nearby points of the separatrix, of the heteroclinic orbit. Okay, this is a bit more technical, and since I don't have much time, I'm just gonna go fast in the sense that it is possible to write also sort of semi-analytica because some of these coefficients need to be estimated by solving the variational equations numerically, but we can obtain this analytical expression that tells us how the variables, how the points on this section are mapped by the system to points on this section J in. Okay, so we applied this with a system consisting of 3 frequencies that are as much incongruent as possible. This is a nice discussion that Carles Simó did in this paper in 16. And we choose Poincaré sections at a distance 0.1 from the saddle points, and we use these external inputs. And then we can have, this is to show that we have an expression for the global map, and this is analytic. So this is just discrete dynamics. And finally, the separatrix maps, which is which is the combination of these four maps. And this provides the dynamics from the section sigma out to itself. Then we want to see that there is chaotic dynamics in this map. Okay, because we want to see, because we're going to have these irregular patterns that I discussed before. So we simulate the system with several initial conditions, and we compute the maximal Lyapunov exponent. For the cases where when we put just one frequency, two incongruent frequencies, or three incongruent frequencies. In all cases, what we see is that the Lyapunov exponent is above 0. So we have a chaotic map, okay? And actually, when we plot the distribution of times, that is the times that we spend close to the vicinity of p equal to 1 or p equal to -1, we observe that as we increase the number of frequencies, the distribution of times resembles more and more to these log normal distributions that are seen in the experiments. This is the same model, but simulated with noise. So these are like these fittings of these distributions with log normal distribution. And what we can see is that for frequencies, as we increase the number of frequencies, these get closer to the distribution that we obtain with noise. So finally, to finish and conclude, is that our main question was like, what is the minimal degree of complexity? Complexity in the sense like how complicated has to be the perturbation to explain switches in bistable perception. We've seen that with two or more non-resonant frequencies, we can obtain gamma or log normal distributions of dominance times similar to the ones observed in the experiments. The thing is that by means of this separatrix map that we've done this analysis, we have provided a discrete model that can be used for models of binocular rivalry, and also I think that it can be extended to other areas, and which avoid integrating the original system, in particular integrating it close to the saddle points, which is computationally expensive. And finally, other related questions that emerge is like this debate about like whatever deterministic models with noise or deterministic chaotic models. So what we get from ones or the others. And finally, other future work possible is like, so this is sort of a toy study. So make it like taking like real data and seeing how we can feed it. Also, what happens if we have systems with more saddle points, because we can escape from the vicinity of one saddle point, but if we have more than two, then we can go either to number 1 or number 3 or number 2, and also extensions to other areas. Thank you very much for your attention.
Okay, thanks so much, Gemma, for your talk. Are there any questions? Okay, so I have one question. So obviously, the brain is one of the most paradigmatic examples of a complex system in biology, and this is regarding how important is noise, because I have no idea about neuroscience, but I think that there are different phenomena in the brain that have a more local aspect or a more global aspect. For example, I am thinking in these full neuron synchronizations, like for example, in epileptic attacks, if I'm not wrong. So for these cases, maybe a deterministic approach perhaps better than to consider stochastic dynamics or noise. So is there a kind of relation between the scale at which phenomena are taking place in the brain with how much noise is involved in these processes?
So, of course, this is a very open question, and I think that each particular case needs its own particular analysis. In some cases, possibly, for instance, in the case that I was explaining of binocular rivalry or perceptual multistability, so there are some studies that they have observed that whenever one of these switches is about to happen, there is an enhancement of in another area of the brain that projects onto this, where these populations might lie, where there has been observed like some oscillations that occur in the so-called gamma range, which is between 30 and 100 hertz. So my point is, depending on the particular problem you are considering, maybe you have more information from the experimental data that provides you that, or maybe that provides information on some areas that project onto the one that you are like modeling, and that you might have some information about how are the inputs, or like how are the the inputs that these areas are sending to the neural populations you are studying. So what I mean is that depending on the particular problem, you might have extra information that can explain the regular oscillations without the need to use noise, because maybe you have information that these oscillations are in some frequency range, and you don't need to consider the full spectrum of frequencies.
Okay, I see. Okay, thank you. So, okay, so there are no more questions. So thanks, Gemma, for your talk. Thanks to all of the speakers of today's session. And tomorrow will be time for theoretical ecology. So we are waiting all of you at 10 a.m. in the morning. So have a nice day and see you tomorrow. Thanks so much.